Last time we talked about the controllability for linear systems. Let me start from here. What is the rank of a matrix? Of a matrix means how many independent columns of a matrix. Like, what's the rank of this matrix? 1. Because there's only one linearly independent columns or rows. Right? You can do Gaussian elimination. If you do Gaussian elimination, you will get this. Right? So only one independent rows. And because this matrix is 2 by 2, okay, so any rank below 2 will not be full rank. Okay, full rank means this has to be 2. Of course, this C matrix, which consists of BAB, okay, will be full rank. So if this system is a 3-dimensional system, A matrix is 3 by 3, then you have to check out a 3 by 3 C matrix and see if the rank is 3. This second example is dimension of 3. So the C matrix, which here is B, AB, and A squared B. Now you should be able to understand why we put B here, AB, and A squared B, right? It's still a little bit not clear because it's hard to give you a physical example of this kind of system. So in the next topic, which is controllability for nonlinear systems, you will be more clear because it's more easier to give you an example. Okay. And the definition for nonlinear system is this f and g could be any nonlinear function of x. So compared to the linear system where it's ax and bu, right? A and b are constants which are not function of x. But now, for example, in this affine system, the x and u are coupling together, right? U can change x dot, right? And x dot can change x, which goes back to here, can change gx. So the gx at t0 is not equal to gx. But before, your B matrix, which is similar to this gx, is constant in a linear system. But here is not constant, it's a function of x. So here's an example for nonlinear systems. There are 2 examples. So the first example, U1 is like the pedal of the car. You can control the linear velocity of the car. And this U1 fixed on this vehicle. No matter how you steer in the car, this U1 is the heading angle. So in the first example, there's only one control input U1, which is the heading velocity. In the second example, we add one more control input U2, which is the steering. You can say angular velocity of this. Okay, so this you can change the direction of your car. In these 2 examples, one is not controllable, so it should be obvious, right? This controllable is we want to, in the linear system, I say if the state is x1, x2, and your control input is u, right? If you can find a way to control every state by this u, the system is controllable, right? Similarly, in here, what are the states? The states are x, y, and theta, right? What is control? Control is U1, U2. So what is controllability? If I can give an external control to guarantee that this state can be affected by this control input or this control input, right? So in other words, if I can change the velocity or steering the car such that you can move to any x, any y, and any theta, right? So what is any x and any y? If I can accelerate and steering my car to move the car to anywhere in this x, y, z plane, any location in the x, y, z plane, that will be controllable. So in this case, is that controllable? Not. Why? You cannot change your steering angle. That means that you can always go in forward and backwards. You can only drive your car anywhere on this straight line. So it's not controllable. Obviously, this one is controllable. If you understand this, then the next question is there any systematic way to check that given the system, a nonlinear control system, and you can use that systematic way to say it's controllable or not? We are lucky is a simple example, right? So here, as I mentioned, given a control input, right, you can change your derivative of states, right? You can change your derivative of states. And as time goes, this x will be integrated. So the x will be different from the previous time. And this x can change the gx, right, in time, delta gx. So the gx is not constant. So this control u can change x, can change f, and can change g. Everything changes. So it's very complicated. In this example, when you see a parking lot in the roadside here, you want to park your car to this roadside parking slot. How will you do that? So what you will do is you first go here and rotate your car to the counterclockwise and move back and rotate clockwise. Then you are in this parking slot, right? These are the combination of your control input. So given this series, it shows that it's controllable in this case. How can you do it in a more systematic ways? So given a nonlinear system, here's a lemma called Lie bracket. And the definition is this y prime is the gradient of y with respect to x. X prime is the gradient of x, capital X, with respect to x. Okay. And the physical meaning is this is the derivative of y along the flow joined by x. You can say the change of y along the change of x. But unfortunately, x is changed based on these dynamics. 这个意思是我 y 会改变多少？如果我改变我的 x 的话，但 x 也不是随便改变的 ，x 必须遵守这个 differential equation， right？ 这是 dynamics 嘛 ？Robot has its dynamics, vehicle has its dynamics. They are different, right? So they are expressed in different ways. So this motion is constrained. The motion of x is constrained, and this x could be g or could be f. Y could be g or f. For example, the controllability for the nonlinear system is taking care of all the brackets involve f or g. Okay, so here is one Lie bracket. Here is another one Lie bracket, and in which there is another Lie bracket. So this will give you a column vector, column vectors, and you check if the combination of this column vector will be full rank. 这个就看成有点像 B, A, B, A square B, and you check if this matrix will be full rank. This example is exactly the same. This example. Okay, so now what is f and g in this system? So you can say the state x is x1, x2, c dot. Three-dimensional column vector. And what is f? So how many control input here? 2, right? So you will have u1 and u2. Okay. So if that definition is okay, given x, what is f? Zero, 对不对？ What is G1? G1 is the coefficient of U1. G1 is the coefficient of the first control input, which will be cosine sine 0, and G2 will be what? Is the coefficient of U2, which is 0, 0, 1. Okay. Let's try F and G1. And you can also try F and G2. So in this case, it's kind of special case of Lec1 because Lec1 only give you one control input, right? But here you have two control input. But assume that you can only control the velocity, the heading velocity of the car, but not the steering velocity. Then you can eliminate this one, which give you only one control input, and that will be exactly the same as the system. But for two control input, it should be similar, and that should be fine, right? So what's this? According to the definition of this D bracket, so the capital X layer will be F, and Y will be G1. So according to the definition, the right-hand side of the definition is partial of Y, right? And in this case, it's G1 times F minus F partial G1, right? So what is G1 partial? It's defined as the gradient of G1 with respect to X, which is the state. Okay. And what's the dimension of G1? 3 by 1, right? And X is 3 by 1, right? So what will be the dimension for this gradient? 好，也会3乘3. Okay, Y. Y is 3 by 3. As you know that gradient of G1 with respect to X times delta X will be delta G, right? 这样对吧? Gradient, and you times some differential of X will be the differential of G, right? Agree, right? What's the dimension of this one? 3, right? 对吧? And what's the dimension of this one? Delta X. X is 3 by 1, R3. 3 by 1, 3 by 1. So it's clear this one had to be 3 by 3. 对不对? Right? We know this one is 3 by 1 and equal to a 3 by 1. The only possibility is 3 by 3, right? Right. So this one will be 3 by 3, which is this one. Okay. And what is x1, x2 theta? x1, x2 theta. x1, x2 theta, because when you times some delta x, right? This one goes to the first column. So all these have to be x1. All these have to be x2. All these have to be theta. Okay? So what is this? It's required in here. So what is gradient of G1? So G11, 1 means that in G1, the first element. G12 is G1, second element. Okay. So G11 cosine theta, right? So cosine theta, cosine theta, cosine theta, which are independent of x1 and x2, so they will be 0, 0. What is cosine theta? Partial cosine theta with respect to theta. Minus sine theta, right? And what is G12? G12 is sine theta. So again, 0, 0. Because they are sine theta independent of x1, x2. This one will be cosine theta. And this is 0. G13 is 0. So it will be 0 for no reason. Okay. So, and what is F? I skip these two. Okay, should be fine, right? So what's this? F1 is, everything is 0. So it will be 0. Okay? So this one is 0. So G1 prime F will be 0. 0. But if that's fine, let's see here. So we have try F G1. You might also want to try F G2. But because F is 0, no matter how you try, will be 0, So you might need to try G1, G2 rather than put F in here. So for G1, G2, if you follow the same procedure, you will get a sine minus cosine 0. Okay. So this D bracket generates the motion in the direction perpendicular to the orientation of the car. So what does this mean? So see, this one is perpendicular to G1, and this is the orientation of a car. But what does this mean? This one means that if you use the combination of this G1 and G2, you drive and steering, you combine these two actions, you will obtain a motion that's called slide. If you use U1 and U2, you can move a car from here to here. It's kind of slide. So here is G1 and G2, which is the coefficient of U1 and U2. And you examine this, and you find a column vector, which the first and second element are non-zero. That means that in these two states, the action, the series of control input, can change these two states in this direction. In this direction, it's kind of like you slice, okay, perpendicular the orientation of the car. Okay, originally your orientation is here, right? But you can move in the perpendicular direction, which is this direction. So you move from here to here. And remember that the Lie bracket means the derivative of y along the flow. Flow means the time derivative of x. And there are some more examples. Let's see. It's a similar dynamics compared to the previous one, except there's one more state. Again, you have U1 and U2, the heading velocity and steering your car for U2, right? Because U2, which here is a non-zero element, which changes the time derivative of theta. Okay, so this U2 is for steering. This one is for acceleration. So G1 and G2 are the corresponding coefficients. So this one is for driving, this one for steering. So if you combine these two, you steer and you drive, you can generate a motion called wiggle. Okay, wiggle is kind of like a snake. And if you combine wiggle with drive, you can slice. So what is controllability? Controllability here is the same definition is accessibility. You have access to all the states by your control input. So how you evaluate if this system is controllable? You need to evaluate if this is full rank. Okay, for example, so this is one column, right? This is one column. One column. Next column will be G1. Okay, this is another column. And in this case, it's 3. This dimension is 3. So at least you need to find 3 combinations of this. So next one will be G2, G1, G2. Okay. The only difference between these two is I put G1 first and G2 first. Okay. And here you should get a 3 by 3 matrix. Check if that's full rank. If that's not full rank, don't give up. Try more. Put more, add it more. Like G1. So the first one will be either G1 or G2, the first one. Okay, never changes. Only 2 possibilities. And the second one could be, you can repeat from the previous stuff. Okay. So all this is trying to say, oh, I use these 2 combinations. 2 combinations of control input. And added one more combination of control input, right? Replace G1 by different combinations and try as more series as you can and see if you got a full rank. If you got full rank, that means you can control, you have accessibility or controllability to any state by using the 2 control input. Here, one more thing you need to remember that because the result of this deep bracket is a function of x3 and x4, right? This value depends on the state. If your x3 or x4 is 0, then this will be 0, and it will be 1, 1. So they always changes according to the states. So maybe in some states, the system is not controllable. So this matrix, in general, will be a function of states. So in some states, it might not be full rank. That means in some states, it's not controllable. You need to be aware of this. And here's another necessary condition. Again, necessary, not sufficient. The deep bracket of f and g cannot be the span of f and g. Otherwise, it will not be controllable. Also, this is another property. If you swap g and f, there will be a minus sign. Okay. That's easy to check, right? So what does this say? It says that if you change the series of your control input, if you apply U1 first, then U2, or U2 first, G2, they don't change too much because the non-zero elements will be non-zero. The difference is the sign, right? So how do you prove this? It should be easy. And you swap according to the definition. This is definition. It will be f g minus g prime f. So what's the difference? It's only the minus of this will be this, right? So when you swap the two, this you just need to add a negative sign. Okay.